Hey guys, it's Miss Johnson, and I am here to bring you our first day of notes for Chapter 5. We are kicking off Chapter 5 in the book, and Chapter 5 is all about probability. So we are gearing up for probability. This is a big chapter. This is an important one for our whole course and for the exam at the end. So here we go. Today we're just talking about the idea of probability, and we're also going to get into simulation, but that's more the second part of chapter 5.1. So the idea of probability is really just chance behavior that is unpredictable in a short run, but has a regular and predictable pattern in the long run. So if you are looking at chance behavior and you're looking at this over just a couple of trials or a couple of times or a couple of instances, it seems really unpredictable and it seems really haphazard and things seem really funny sometimes. But the longer you repeat an experiment or a trial or something, the more trials you do, the more predictable the behavior comes. So if you take a look at this little graph of these figures here, the first figure on the left, you're talking about flipping a coin. They're looking at flipping a coin here. And what is the probability of getting heads when they flip the coin? Okay, so this graph on the left, if you look at it, it's pretty haphazard. So the first flip, they got a heads, that's 100% probability. The second flip, they must have gotten a tails because now they're at a 50% probability. The third flip, they got a heads, they're up at 66%. The fourth flip, they got a tails, so they're back at 50. The fifth flip, they got a tails, so they're down at 40%. And you can see, and it kind of bounces around, okay? They only flipped the coin 10 times here. So their probability bounced quite a bit because they didn't do very many trials. Now, take a look at the second graph, the graph over here on the right-hand side. Their number of trials increased to 500. So they flipped the coin 500 times. Now, you and I know there are two sides to a coin. The true probability of flipping heads is 50%. We know that. We know that there are two options. So getting heads out of two options, that's 1 out of 2, which is 50%. If you take a look at what happens here when they repeat their trials, they're up really high, then they're down really low, then they're up and they're up and they're up and they're bouncing around. And the more trials they complete, the closer they get to that 50% mark, which we know is the true actual probability. So that's kind of the idea here. Your random chance is unpredictable. Random chance, we don't know what's going to happen. But if we look at this, a simulation of something repeated over and over and over and over and over again, the more we repeat that, the closer we're going to get to our true actual probability. So the probability of any outcome of a chance process is the number between 0 and 1 that describes the proportion of times the outcome will occur in a very long series of repetitions. So again, the more you repeat something, the more you get to the true probability. That probability is always between 0 and 1. Okay, you're looking at some sort of proportion or some decimal. A lot of people turn that into a percent. You're not going to see that so much in AP stats, but you can think of it in terms of percent. 50% of the time when I flip a coin, I'm going to get heads. Now we know that it may not actually be 50% of the time. I may end up with a probability overall in my lifetime of flipping coins that's a little bit different from 50%. But we know that the more times we flip the coin, the closer we're going to get to that true 50% mark, just like these 500 trials here. So the law of large numbers, okay? The law of large numbers tells us that if we observe more and more and more repetitions of any chance process, the proportion of the times that the specific outcome occurs approaches its true probability. So that's what you're seeing here. The true probability of flipping heads is 50%. The more and more times we repeated it, the closer it got to that true probability of 50%. Okay, let's just talk a little bit more about randomness. The idea of probability is that randomness is predictable in the long run. Unfortunately, our intuition about chance behavior tries to tell us that randomness should also be predictable in the short run. That's not always the case. I may flip a coin 3 times and get tails all 3 times. Then my probability of getting heads is 0. But we know that that's a possibility. Of course it's a possibility. But that's why we can't use the short run to predict our probability. We don't want to predict our probability in the short one. We want to predict our probability over the long life or the long run of all these trials. It says some people use the phrase a law of averages to refer to the misguided belief that the results of chance process have to even out in the short run. But that's not actually true. We need to be really careful there because randomness tells us that I can get a random result each time I flip that coin. If I only flip the coin 3 times, it's very possible that I don't get a heads, or maybe I only get 1 heads and then my probability is 33%. But if I do it over the long run, that's when I'm going to start to approach that true probability. So calculating probability is simply a measure or estimation of how likely it is something will occur. It's a value between 0 and 1, which we talked about. The higher the value, the more likely the event. That seems obvious. You're going to see notation that looks like this, P of A. And then your true probability ratio is just the number of successes divided by the total number of possible outcomes. So for flipping a coin, it's 1 out of 2. Flipping a heads, I should say. Heads, there's 1 option. Total options, there's 2. 1 out of 2. All right, so very basic probability. If we calculate the following probabilities, you have a bag of 3 red, 2 green, and 5 blue marbles. How many total marbles do you have? You have 10 total. So if we find the probability of a blue marble, that means I'm looking at the number of blue divided by the number total, which in this case is 5 out of 10, which is 1 out of 2, or in other words, 0.5. You will most often see probability written as a decimal. If I look at the probability of green marble, that means I'm looking at the number of green out of the total, which is 2 out of 10, or in other words, 1 out of 5, or in other words, 0.2. Okay, that's the probability of green marble. This third one, find the probability of red or green, or tells me that I have multiple successes and I need to add them together. So that means I'm looking at red plus green divided by total. So in this case, that's 3 plus 2 over the 10, which is 5 out of 10, or in other words, 0.5. So those are just very basic instances of probability. This is nothing to do with simulation. This is just basic probability. Successes to total. You're always thinking successes to total. So if we think about a standard number cube, or in other words, a die, we're looking at the probability of 3. If you think about a number cube, the options are 1, 2, 3, 4, 5, and 6. There are 6 options, and each one only occurs 1 time. So the probability of rolling a 3 is 1 out of 6, or in other words, 0.167 if I round that out to the 3rd decimal place, which is typically what we do with probability. In part B, it says probability of a number less than 5. The numbers less than 5 are 1, 2, 3, and 4. So that's 4 out of 6, or in other words, 2/3, or in other words, 0.667. Again, we typically round probability out to the 3rd decimal place. A multiple of 2. Multiples of 2, there are 3 of them. 2, 4, and 6, that's 3 out of 6, or in other words, 0.5, 1/2. A number greater than 6. 6 is my highest number. There is nothing greater than that, so that's 0 out of 6, or in other words, 0. No chance of that happening. Let's talk about a deck of cards. Calculate the following probabilities from a deck of cards. So if I want, here's a picture of a deck of cards in case you're not familiar with it. There are 4 suits: clubs, hearts, spades, and diamonds. Half of the cards are red, half of the cards are black. These cards right here are face cards. They have faces on them, literally. People get confused with aces, but aces do not have faces, so they are not considered face cards. There you go. All right, so the probability of a selecting a 4. If I pick 1 card out of the deck, what's the probability I get a 4? In this case, there are 4 4s, so that's 4. There are a total of 52 cards. I probably should have said that up when I was describing it, but 4 out of 52 is the same thing as 1 out of 13, and if I plug that into my calculator, which I didn't have out before, sorry, I'll get that now. 1 out of 13 is 0.077. So about roughly 0.077 for probability there. How about the probability of a face card? If I think about face cards, there's 1, 2, 3 in each suit times four suits. That's 12 face cards out of 52 cards. That's almost a quarter, but not quite. 0.231 there. Technically, I'm rounding these, so I probably should use approximately equal to, but this, by the way, is not something that you would be docked on the AP exam. If you used an equal sign instead of approximately equal to, you will not lose credit on the AP exam, so you're good there. Probability of red. Half the deck is red. Literally 26 of the cards out of 52 of the cards are red, and that is exactly 0.5. That's a true equal sign right there. Probability of a red king. Red king. Take a look. There's 1, there's 2. That's it. So 2 cards out of 52 are red kings. 2 divided by 52 is 0.038 there. 0.038. for probability. So those are just some real basic examples of probability. Remember that we're talking about random chance here. And random chance is exactly what it says. It's random. We don't know what's going to happen when we do these things 1 time or 2 times or 3 times. But what we are going to do in AP Stats is we are going to repeat experiments lots and lots of times, because we now are learning that the more times we repeat an experiment, the closer we get to a true population probability. And that's the goal. We want to reach a true population probability, so we have to repeat experiments. And we will talk more about that in our next lesson when we talk about simulation. Thanks for tuning in. I will catch you next time.